Hello, good afternoon. So welcome again to the ninth webinar on ML4LM. And today we are touching upon the hybrid modeling for land with Professor Andrew Bennett. And Andrew is an assistant professor in the Department of Hydrology and Atmospheric Science at the University of Arizona. And his research focus on developing machine learning technique on hydrology across a different range of scales and processes. And prior to that, he got his PhD at the Civil and Environmental Engineering from the University of Washington in 2021, and worked as an associate researcher in the Computer Science and Mathematics Division in the Oak Ridge National Laboratory. Besides that, he have written several paper on the land modeling and hydrological modeling, but also combined with the machine learning. So that's very fit for our webinar. And I would give the floor to Andrew for his presentation. Thank you, Andrew.
Yeah, excellent. Thank you, Suhail. I started out with a bit of a generic title here that's just hybrid modeling for land. But when kind of putting it together and thinking about what I wanted to talk about was how we might develop new modeling techniques in the age of AI. So with that, let me there we go. Yes, so hello everyone. Thank you, Suhail, for the really nice introduction. You basically got all of this, but I'll just state that, in addition to my background in hydrology and hydrologic modeling, I've done a lot of programming and data science and have a lot of interest in developing new models for land surface modeling broadly. So just continuing on, uh, when we think about land surface models, I'm using this sort of um, in the terminology of like critical zones, so everything from groundwater up to vegetation. When we think about how these models were developed for especially large scale modeling, starting in like the 1970s, we were mostly interested sort of in the idea of these models being a lower boundary condition for atmospheric models and sort of climate models. And then as people started to develop more and more specialized interests in understanding certain feedbacks, people would add in all of these different modules. And here we go. Okay, just grabbing my mouse. Um, so we started to add things like soil moisture and plant interactions, and all the way up, now we're doing, land cover, land use change, human impacts like urbanization and crops and all of this. And it wasn't so much that these were just independent models that were developed and used on their own. It was really sort of this rich ecosystem that started to make a more holistic understanding of the land surface. And so I think this sort of backdrop and understanding that, we were using these models in a way that you could probe multiple hypotheses, you could look at interactions and things, is really important when contrasting it now with some of the development of machine learning stuff. So now switching to sort of more modern era in the age of AI. So as far as hydrology goes, I think one of the like really big watershed moments starts to happen around 2017 to 2019, where and I think it's fairly uncontroversial to say that Freddie Kratzer's set of original LSTM papers uh, for doing rainfall runoff modeling were really sort of the moment where machine learning really took off in hydrology. And so these first two papers that I kind of have on the left here are some of the really important early papers where Freddie and his colleagues found that these LSTMs, it's a recurrent neural network type of model, were able to outperform uh, traditional hydrologic models for rainfall runoff predictions. And not just that they could outperform them, but they could also generalize to sites that were not in the training data. And this kicked off what I would say is a really huge amount of research um, and really upped our capabilities in terms of being able to make predictions for streamflow modeling in particular. And these papers and these modeling techniques have been used across a wide range of hydrologic processes as well. Um, so this is kind of where I say this all kind of kicked off and became really exciting. And it's not just that when I say all aboard the hype train, I don't mean that there's no that there's not like um, real capabilities here. These models are really good. Like there's no denying it. So here's two cases for uh, streamflow prediction where this LSTM type model are really like a huge amount above all of our other models. So on the left here, we have the Great Lakes Runoff Intercomparison Project, and you can see that this LSTM model is uh, is showing sort of top of the pack and where a higher number here on the right of this figure is better. And basically what we see is like, it's not just better, it's like significantly better than all of the other models for runoff prediction that were included in the intercomparison project. And similarly, there is a company called Upstream Tech that does streamflow forecasting, and they won a forecasting competition that was put on by the Bureau of Reclamation here in the US. And it was not just that they won the forecast competition in general, but they won across every single category that they put their model into. And their model is also one of these LSTM type models. So again, these are like really good models for making predictions. And it does sort of beg the question going back, why do we have all of these other models? And what does it say about all of the hydrologic science that we've done before? And going forward, if these models are going to be so good, what do we need to do as hydrologists and, land surface modelers to not only take advantage of this, but also to contend with the fact that sort of data-driven models are so much more predictive. And so that's kind of what I want to talk about. And I should say it's not just in hydrology, of course. I'm sure many of you are coming from other aspects of the earth sciences at large. And of course, these are honestly, these are a little bit out of date at this point. But there are really huge uptake of these types of models in atmospheric science and weather prediction as well. And so here I'm just showing two examples where these deep learning models are used for weather prediction, even going out as far as like weeks 5 and 6. And we've seen, I'm sure many of you are more up on this than me even, but, we've seen ECMWF has its own AI model. NVIDIA is coming out with its own models. They're making these big press releases and showing really strong performance. So this is something I think writ large across the earth sciences that we're coming to, uh, see these models as not just um, not just working in one domain, but across the board. So as you can imagine, there's been an explosion of these sort of applications, pretty much all showing that if you have the data, you can make a model that works really well with these deep learning type systems. So hydrology going back in 2023, there was almost 1,000 papers using this LSTM type model. And that's, again, just one specialized type of neural network model. There are many other architectures that people use. And of course, now, in the age of ChatGPT and things like that, we're seeing transformers and diffusion models sort of take over. But again, I just want to highlight how popular these methods are and how easy it is to apply them once you have a data set that you have a question that you're interested in. So the thing that I started thinking about a little bit more was um, if we all have our models that we can take and apply and write our papers, um, that's really great. It really adds scientific value to be able to make these predictions better. But as a modeling community, I think once you have these powerful tools and your data sets, it kind of starts to end up being where everyone now has their own little favorite ML model for their favorite data set and their favorite problems. So I think this sort of is an interesting thing to think about in terms of fragmentation uh, of the processes that we know interact at the land surface. And I think there are many ways that these tools are, breaking apart these processes, but now as a community, we're sort of starting to figure out how to put them back together and incorporate things like multiple processes or representations that are a little bit more flexible. And so I wanted to talk about a couple ways that I am starting to look at that in terms of land surface modeling in particular. And there are, again, big efforts across multiple organizations and groups, like the Climate Modeling Alliance or the LEAP STC here in the US. There's also private investment in some of these types of things, like the Allen Institute for AI has a climate modeling group. So does NVIDIA and Google, as I mentioned. So there are a lot of efforts here. So I'm not trying to say that I'm the only person working on this. I think it's a really exciting space to be in. And for those of you who are also in this area, thank you for joining. So I'll just go ahead and talk about some of my efforts to sort of bring back some of the more traditional physically based modeling approaches or finding ways that they still fit into the world given AI predictions capabilities. So I'm going to showcase, I think, three what I call them case studies for these physics-based ML and hydrology. Sorry. And the first one is going to be sort of under the idea of model emulation to sort of speed up simulations that we don't have sort of non-physics-based model alternatives. So what we're doing in this case study here is emulating the Parflow CLM model to try to speed up its computations. So this work is in collaboration with Laura Condon, who's also at University of Arizona, and then also Reed Maxwell and Peter Melchior at Princeton. And in terms of land surface modeling, integrated hydrologic modeling is one of those areas where we think we understand the physics pretty well, but we don't have enough data to really constrain our models. And the models are very computationally expensive. So what we're doing in integrated hydrologic modeling is really taking a holistic viewpoint where we have a total model representation that goes sort of from the bedrock all the way up to vegetation. We're covering everything in the water and energy balance, and we have variably saturated flow. We don't impose like a river network. We allow the model to come up with its own overland flow based on what's happening in the subsurface and what's happening with the land surface as well. So you can imagine that this is something that when you scale up to large areas. So in this case, we're working on this sort of cookie cutter on the contiguous US. When you scale this up, this becomes a really challenging computational problem. So in this case, what we're using is a 1 kilometer grid scale. So this is about 2,000 by 3,000 kilometers. And so that ends up being 6,000 grid cells, or if you include the 3D, so including depth, we have was it about 30,000 grid boxes in the domain. So it's a very large model, and we're resolving that full spatiotemporal dynamics. So it's 3D, it's got time. And as you can sort of see in this picture, I'm just showing the water table depth from the original simulations. You can see it spans orders of magnitude. And you can see these really strong spatial gradients, particularly in the Western US, where you have a lot of variability. So this is a challenging process to simulate. And if we want to use sort of these types of models to do forecasting, it becomes challenging because the simulations take so long that you might as well just wait and see what happens. So what we wanted to do was similar to how some of the weather prediction models leverage AI, is use historic simulations to train a model that can then make future predictions. And so that's really what we're doing here. In this study, what we did was of course, you have to start with some baseline architectures. And so we're using a ResNet and a UNet. So the ResNet is a convolutional neural network that has these sort of blocks of convolutional features and then a residual connection. And then eventually, after some repeated number of these blocks, you have your output. The UNet is also a convolutional neural network, but it takes into account different scales of spatial variability by doing downsampling and then upsampling through its blocks. And those blocks are also just stacks of convolutions, essentially. Of course, because I said we're testing against baseline architectures, what we found was those didn't quite give us as much performance as we wanted. So one of the things that I did in the study was I developed, I call it a new neural network architecture, but it's really just a rearrangement of existing components. And it works very simple or very similarly to how you would conceptualize a hydrologic model, where it takes initial conditions and its parameter values, things like the hydraulic conductivity and so forth. And initializes the model using two encoders, a memory encoder and a cell state encoder, which are just their own convolutional neural networks. And then once initialized its memory states, you use the weather forcing, so the temperature and the precipitation and all of that, as an external forcing on the system. And then internal to it, it is a variant of a convolutional LSTM that has sort of a couple extra pieces. So it has these M and C pieces are the two different memory channels. One is temporal memory and one is spatial memory, you can think of it as. And then it just runs in an auto-regressive setting where outputs from one time step feedback in and are aided to predict the next time step. So this conceptually is very nice because it looks a lot like your standard hydrologic model. It just has, big matrix multiplies instead of nonlinear solves on the insides. So, of course, the implication of me telling you all of that is that it works better than the other two models. So here's just the RMSE in terms of the long-term water table depth error across the modeling domain. So the ResNet actually does work pretty well. It has sort of a higher error, I would say, in the east part of the US compared to the FSTR model. And the UNet sort of has a higher characteristic error across the board. You can get the UNet to work a bit better, but it does tend to be more unstable. So one of the things that we found was when training these models, you have to run them auto-regressively in all cases. And the UNet model tended to be the one that when it went off the rails, it would do it in sort of a catastrophic way. The other models, eventually, if you run them for long enough periods of time, they will do the same. But this is after a 1 year rollout. So these models look quite good. And the other thing I should note about this result is that in the Western US, you can see that all of the models do somewhat poorly. We're or appear to. We have very deep water table depths in the Western US where there's a lot more aridity. So these models actually show pretty consistent good performance across the entire domain. Um, and I just want to highlight that by showing this two sets of figures um, where I show both the temporal variability and spatial variability. So this is just showing the pressure head in the subsurface across the 5 different depth layers of the model. And the blue line is the Parflow predictions and the orange line is the emulator prediction. So you can see it matches the seasonal cycle really well. And you might think that doesn't match exactly. The thing I want to note is this is just like a random grid cell out of the 3 million in the domain. So this is actually a really good match, and pretty much anywhere you pick show these really strong correlations. And similarly, this is on the right, the spatial variability. I just took a little cookie cutter from the center of the domain and showing again each of the 5 depth layers in the model and the prediction or the Parflow predicted, the emulator predicted, and then the difference. And you can see this is at the end of a 365-day rollout. And what you see is it holds on to those spatial patterns really well. So this is really good at reproducing Parflow CLM simulations. And the thing that is most exciting about this, I think, is that a, a full 1 year rollout of this takes about 30 minutes on a GPU. We were using A100s for this, so a fairly beefy GPU, but still 30 minutes for 1 year to run continental scale groundwater models is really good. And what we found was this was about a little bit more than 100 times speed up compared to the original simulations when they were running on over 3,000 cores. So again, really, really striking speed up. And this is enabling all sorts of other things that we're currently still working on. So one of them is simulation-based inference to calibrate these types of models. So once you have a fast emulator, you can start to vary the parameter values and try to match um, your observations better. This is still a really challenging thing because, again, we have sparse observations and we need to make sure that the sensitivity to parameters is correct. So we have one paper out on this that was done by one of Laura Condon's students, and you can check that out. And we have a ton of ongoing work on this front. You can also try to do other things like large-scale parameter inversion. And this was another paper that we did on this, where we basically used an ensemble of different parameter values, particularly hydraulic conductivity, and try to instead think of it as a forward emulator, think of it as an inverse emulator, where you try and come up with the parameter values given some observations or simulations. And that also worked really well. And so once you kind of have this framework, you can start to do a lot of really exciting things. So this is where using a physically based model and a set of machine learning models, you can actually do more than you could with each independently. And I think that's a really cool idea. So the key takeaways from this was that the model emulation can yield multiple orders of magnitude speed up, and this enables a ton of knock-on things like ensemble methods, on-demand forecasting, parameter estimation, calibration, and so forth. And I think this is also a really nice way to just play with models because it works so fast. So I think it's something that if you haven't played around with, I urge you to give model emulation a try, because yeah, you can just do a lot more with your models. So moving a little bit more towards explicitly hybridizing things, I'm going to talk about another case study where we actually parameterized a process inside of a hydrologic model with a neural network. And this was a part of my PhD work with Bart Nyssen at the University of Washington. And our basic idea at the time was, well, we know some processes we don't have strong predictive and well understood parameterizations for. One of those is the turbulent heat fluxes, so sensible and latent heat fluxes. And what we did here was we took a hydrologic model called SUMA, which has a very flexible sort of uh, process representation. We just took the turbulent heat flux piece of it and replaced it with multiple variations. So SA is the first one, which we call standalone, and this takes in the inputs needed to run the calculations, and it outputs the latent and sensible heat fluxes. Um, and this is how the model would work out of the box. We did this and we calibrated it to each of the sites, which I'll show in a moment, kind of giving us our baseline run. So SA is for standalone and it's our baseline run. The next option we did was NN1W, which stands for one way. It only took in model parameter values and meteorological forcings to make predictions of the latent and sensible heat. And then you can imagine that this only taking in forcings, it can't see all the other processes, all the other states and fluxes that are happening inside the hydrologic model. So the second variation that we used was NN2W, which takes in dynamically calculated states from the rest of the model. So it knew kind of what sort of soil storage was there, and things like that. So doing this experiment, we were using 60 FluxNet sites shown here. We had pretty good coverage of the sort of different ecosystems in the data set, and we had over 500 site years on a half-hourly timescale. The neural network methods ended up being more predictive than the process-based parameterization. So here what I'm showing is a KG, which is just a performance measure where a higher value is better and it caps out at 1. So any curve that falls to the right is better in this case. And so what we see is the SA method, which was calibrated per site, does not perform as well as either of the neural network versions, which were trained across the entire domain, and then we did a spatial holdout. The other thing that you kind of can eyeball here is that both neural networks kind of do similarly. You could argue that it does a little bit better on the latent heat. And we looked into that. And one of the interesting things that we found was adding that two-way coupling actually ended up improving the long-term water balance in our modeling efforts. So here I'm showing the observed evaporative fraction, so the total ET over the total precipitation compared with the simulated for each of the methods for each of the sites. So each dot is a site in this case. And they're colored by their predictive performance, essentially. So a redder dot is a better model. And for SA, what we see is we tend to fall pretty close to the one-to-one line with some under, I guess, evaporation. And then the NN1W kind of falls on both sides, and that's sort of because it doesn't know how much water is available to evaporate. It only ever sees the meteorological forcings. So when we add in it's not a constraint, but when we add in the information to the model about the soil moisture states, it actually learns a little bit better how to self-constrain. So you see less over evaporation in this case. And that's where the NN2W ended up being better on latent heat, which is the energetic counterpart to evaporation. So we found that was a fairly interesting takeaway to this. Um, one of the things about this was when we allowed the model components to talk to each other, we ended up with like these emergent improvements, which I think was to us, I guess the more interesting part than just neural network does better prediction. And having a better sense of those land atmosphere interactions improves, your ability to simulate the long-term water balance, which is something that hydrologists are always interested in. The last thing that I'll say about this was SUMA is written in Fortran, and our models were written, or our neural network models were written in Python. So this became a fairly like hard and painful exercise of coupling these two things that it's not just making Python talk to Fortran. It's also the brittle coupling of a data-driven model with something that has very strict numerics for solving the differential equations. So I think one thing that we don't have a ton of technology for is being able to use our legacy models of the hydrologic system with these new techniques. And that's something that is going to create a good deal of work for us in the future. And so moving just towards where I think a lot of us are currently thinking, and there's a ton of cool work happening, is really these truly hybridized models, which kind of allow us to more systematically and more easily couple traditional physics-based models um, with these machine learning methods. So taking 1 second here. I have a few different small experiments here, and they all sort of are in the realm of differentiable modeling. And for those of you who aren't as familiar with this, I highly recommend you check out this paper by Xiaopeng Shen on differential modeling, sort of at large. But the basic idea of this is you encode all of the equations that you want in a framework that is differentiable, which sort of drives a lot of the ability to run gradient descent and train neural network models. And then you can essentially replace, you can have some physics equations, maybe ones for precipitation or snowpack, but the parts that you're not as sure of in terms of the physics, you can either replace with a neural network to do that whole process on its own, or you can replace the parameter values with a parameterization technique that would be a machine learning model. So there's multiple ways that this can be arranged. And essentially what you do is you pick and choose where your hypotheses need to be replaced with data-driven techniques. So the first part of this sort of section is mostly done by my students, Amir and Nabin. And then I have a part that I've been leading up in collaboration with Freddie Kretzer and Walter Knoben. So I think with that, we can just jump forward. For those of you who are really not as familiar with this, I think maybe a simple example is really a nice way to do this. So if we have a nonlinear reservoir sort of equation, so the change in storage over time is some function of conductivity, which depends on the current storage times the storage. And so I just came up with this simple curve here where essentially what happens is the model wants to reach some equilibrium storage amount. So if you have too much water in the tank, it drains out. If you have not enough water in the tank, it starts to fill up, is essentially what happens with this curve. And then you can train a model instead, if if you suppose you didn't know the that conductivity term, you would replace it with a small neural network, and you would give it examples of the trajectories from that system. And then when you do that, what you can do is you train on just a small subset of these points. So just taking, I think this is about 10 points across 8 points um, across the sort of range of examples of the conductivity function, and you train a model, you can come up with a fairly good fit to that. And then this can predict your dynamics going forwards. So this is kind of the idea here. And if you want like a hands-on version of this, I have a book chapter here that has a Jupyter notebook that runs through all of the theory behind this, how you can combine sort of your standard numerical methods and its connections to training neural networks. And you end up with a model that takes in catchment attributes and predicts the parameters for a simple hydrologic model that ends up working pretty well on the test basin. So here it gets an NSE of 0.71, and you can see the predictions in red match the observations in black pretty well. So it's a nice little hands-on example. I encourage you to check it out if you want to play with this stuff in a very simplified setting. So with the sort of entire framework laid out, we are applying this method to multiple processes, as are many other folks. So this work is led by my student Amir, and he has parameterized the SNO 17 model with an LSTM. Again, that's just a recurrent neural network type model to predict the parameters of a the SNO 17 model and predict snowpack across the Western US. So here you can see the model is working really well. We're getting very high performance uh, metrics. It shows a pretty strong improvement over the standard SNO 17 model. Here you can see again, curve falling to the right is better. So the SNO 17 parameterized by the LSTM works really well. And it's not just that it works really well in terms of the standard performance metrics, but it also does a really good job of capturing some key things that we're interested in. So things like the timing of the peaks, the actual peak snowpack amounts, things like when the melting is going to occur and all of that. So this is proving really predictively strong. We also have compared it to a standard LSTM at this point, and it's, as you add more constraints into the model by parameterizing it according to SNO 17, you do lose a little bit of performance in some cases, and so it's really a question of how much constraints you want to add into the model. Additionally, we're applying this, we're going back and looking at the land-atmosphere interaction. So as I mentioned in part 2, it was really hard to get the neural networks to play nicely with the SUMA model. So what we're going back and we're thinking about now is hybridizing this more directly and taking a model that has both energy and water balance, but is written in a machine learning framework. We're using JAX in this case. We can then model all of the main processes with parameterizations that we feel are fairly robust, and then replace the land atmosphere interactions with again, we're just using an LSTM here. It's sort of the workhorse at this point, although we can use other models as well. So Nabin has been doing this for a bunch of FluxNet sites, and we're finding good performance there as well. Here you can see the sensible and latent heat flux predictions at a site and sort of a scatter plot across many different observations. One of the things that's really become interesting in this work is having half-hourly predictions of something that's very dependent on the internal states of the model starts to become tricky when thinking about model initialization and spin up. So if you're interested in those types of things, I'd be really interested to talk and hear about your different ways of handling that type of it's really choice dependent, we've found. So one thing that I think, you see these types of models and you go like, whoa, that works really well. That's really interesting and cool. But it does sort of beg some larger philosophical questions. And so one of the things that happens is people are using these parameterization techniques to have time-dependent parameters. So in this case, if you have a watershed model that uses standard state equations where your storage and time is a function of the storage, the inputs, and the parameters. If you start to allow these parameters to vary in time, which traditional hydrologic models weren't doing, but we're now starting to use these machine learning methods to do. Um, how much of the predictive performance is actually coming from this part versus the hydrologic model parts, which is these three in the bottom, for instance? So that's what we're doing in this last part of this study before I wrap up. And so what we're doing is we're taking a frozen LSTM that was trained across catchments across the US, and then we're replacing just the last piece, which would normally predict the stream flow, and we're replacing it with a separate layer that predicts these parameter values. And we're using three different hydrologic models, and we do these separately. So there's a very simple one storage model, a two storage model, and then a four state model, which is the most complex. So I think these have it's like three or four parameters. I think this one has about six and this one has about nine. So you can see we have three different levels of complexity, but they're all driven by the exact same model under the hood. And we're doing this for 140 camels catchments. Essentially, none of these have a snow model, so we had to choose sites that don't have snow. And when we do this, the figures here are showing each of the three different models and their performance across those 140 sites. What we see is the very simple model never really achieves great performance. It's not bad. It's kind of what you would expect a model of slightly more complexity than this to do. Like it's somewhat surprising that it gets kgs in the 0.4, 0.5 range. And the three different sets of lines, we did this for 10 replicants across the modeling. So we had part static, which fixes the storage amounts, and that's going to be the same across each of these different model types. Is part static means there's one fixed value for the total storage. The all dynamic allows that storage to grow and shrink. And then the fine-tune LSTM was when we actually started to retrain the LSTM model to work with each individual model. So the blue and orange curves all share the exact same one trained LSTM behind the scenes. When we move to the slightly more complex model, you see this one needs that flexible storage to give you really good performance. And this last model really worked well across the board. So this is showing that the same LSTM can predict pretty well for a range of scenarios and a range of model types, which is fairly interesting. One of the other things that we were thinking about was um, if we're allowing these parameter values to vary in time and we've got these 10 setups, are the models learning the same thing each time or are they learning different things? So what we did here is we calculated the correlation. So for each parameter value, we have a time series of its predictions, and we have 10 of those for each of those model replicants. So what we're doing is calculating the correlation, essentially asking the question, is the parameter value evolution the same in each model? And so what we see is here I'm showing the correlation coefficient for every pair of those 10 parameter time series. And so for the simple model, they show fairly good parameter convergence, but because the model wasn't very good, I'm not sure that this is all that interesting. Here's where things start to get a little bit more interesting, though. In the case of the two-state model, um, we see that there is quite a bit of parameter disagreement. You see, correlation coefficients for some of these parameter values. Each of the violin plots is a separate parameter value. You see correlation averages like zero point 0.2, zero point 0.3. And so it's showing that these models are learning many different ways to get the same answer. Because again, going back to this plot, there's not a lot of wide variance in terms of the 10 different models, in terms of their performance. But we are seeing that they are showing a lot of variance in terms of how they get to that answer. So this is something we need to be a little bit careful about. It's nothing new. It's the same old equifinality problem. But ideally, our models should be able to handle this a little bit more robustly. So going to this last, the four-state model, we see that there's actually really good parameter convergence across the different parameter values. And there's a couple that I excluded just to fit it on the plot, but it looks like this kind of across the board. So one of the things that I think is kind of interesting about this methodology is we can sort of ask, like, is there a more appropriate model type for the processes that we're interested in? Because I would argue the model that tends to produce the same parameter values across many different runs is a better model. It represents the processes in a more parsimonious way. So in this case, the four storage model is a little bit more robust and interpretable because you can trust that if you do the experiment again, you'll get the same parameter values, or at least very similar. So there's kind of two big things that I think are also additional takeaways. Um, it's interesting that the LSTM was able to perform really well across a wide range of hydrologic conditions and model types. So I think the LSTM is learning general hydrologic concepts that can be repurposed and reused when you attach it to different models. I also think that the LSTM kind of this set of experiments shows that the LSTM is probably the thing that's driving a lot of the predictive performance. Some of those conceptual rainfall runoff models were very simple and probably shouldn't be able to predict the runoff response as well as it did. So the LSTM is really driving a lot of that performance, I think. And these have been relatively simple methods, especially on the process level. So the hydrology and the energy balance is very simple in all of these models. And as we continue to develop more robust models, I think we're moving back towards having that multi-process representation that I was talking about at the very beginning. So I think this is a really exciting space to work in. And with that, I will wrap up and take some time for questions.
Thank you very much, Andrew. There are a few questions in the Q&A section, so if you would like to answer them.
Is that separate than the chat? Oh, no, it is separate than the chat.
QA, yeah.
I got it. Okay. Okay, so the first question was slide 21, the higher RMSE in the Western US. Oops. The higher RMSE is just because the water tables are deeper. So if you kind of like normalize this by the actual water table depth, here you can actually see what the water table depth looks like. If you normalize it by that, it kind of evens out. So it's really just an artifact of the Western US being more arid. Um, how can overfitting in parameter estimation and the possibility of limited extrapolation be mitigated? I don't really know exactly the answer to that question. And it's one of those areas where I think old and new coming together, we find the same challenges. So one of the things, and this kind of can be discussed in many ways, when we're talking about like simulation-based inference here, where we have an emulator and then we want to use it to calibrate our model, you have to make sure the parameter sensitivities are right. And it's hard to know when you get into a regime where your model starts to not behave well. And that's something that we've had some discussions about, but honestly, I don't know if there's like generalized methods for. If someone knows the answer to like, knowing how to know when your model is not going to extrapolate well, I would love to hear some methods for that because I'm very interested in it. Um, okay, so let me read this one out. Question about hydrologic or hybrid modeling for land processes. We often expect combining them not only speeds up computation, but improves real-world prediction and generalizability. In practice, we tend not to, we tend to focus on the predictive performance and not examine what the hybrid model learns. So, I think this is a great question, especially sort of this last part of like, are we at a stage where we can really even examine, these are highly over parameterized models with, tons of parameter values. And I think this kind of goes to a couple small and separate things. So on one hand, these hybrid models allow you to inspect, other processes that you're not training it to. So in this very simple case, we train it to predict stream flow, but it represents other things. So we can see the storage components, we can see the actual ET versus the PET. I think it lends some confidence that the model is doing something sensible when you can inspect the internal states of the model that are things that we can understand. I think that lends some confidence. However, I will also back that off and say, again, we don't necessarily know, like in this second model's case, it seems like the LSTM is just wagging the hydrologic model as hard as it can to get good predictive performance. So I do think it is a double-edged sword there, and as far as I know, we don't have any, robust ways to know which of the cases is happening. So I think that's a really exciting area. So yeah, thank you for that question. Um, awesome. Yeah, and thank you, Ben. Cool. Any other questions?
Well, I may have one, Andrew.
Please, yeah.
I mean, the last case you showed with the model that is more complex, does it hint that having more process, like physical process, is usually more prone to give better results? And then that brings us back to the physically modeling.
Yeah, that's a good question. We were honestly a little bit surprised that the four-state model was more parsimonious than the two-state model. I I don't have a formal, answer to, how much complexity should we add back in, but I do think that's going to be an interesting question. Um, One of the things that I wish I had more time to talk about, two of the processes in this four-state model are actually like very complementary. So it's actually what we ended up finding was the model sort of learned to treat those two processes as like uh, it would do one of two things, but they would be like complementarily flipped. Um, so in this case, actually, there's one part where adding more complexity gave the model more maybe physical realism, but it also gave it, more opportunity to do things that we probably didn't want the model to do. Um, I think that's a really interesting question. And we're looking at conceptual, bucket-based models. I think when you start to add in things that are a little bit more physically inspired, like um, like redistribution that's based on pressure heads or whatever, it becomes a little bit more rigorously constrained. So um, I think these really conceptual models, it's hard to draw really uh, too much conclusion about where the future will go. I think, at some point you'll either find a plateau or who knows. Yeah.
Yeah, thank you very much for that, Andrew. Yeah, that brings me also to your I think first example where you are mentioning the two-way coupling was performing better, and that is again I think a kind of a proof that the physical modeling is still holding some place there. Yeah, I'm trying, yeah, being biased toward the physical processes and the modeling in that direction. But yeah, obviously this is a great avenue for the future. And I would like to thank you very much for your great talk.
Yeah, thank you.
And with this, I think we have the hour closed. And I would also thank all the attendees for their patience with us, and see you in the next webinar.
Awesome. Thank you again. Yeah.
Thank you.